pleasure to introduce Dan Schwartz, who's a professor of education at Stanford University. This is Dan's. Magically already switched. They look the same, but how are they different? Let's go look. And he's on the leadership team of the Learning in Informal and Formal Environments Center. That's another one of these science of learning centers funded by NSF. If Dedra Gentner is the matriarch of research on learning and analogy, then mentally I have Dan Schwartz as the crazy, crafty uncle of research in this area. He's really consistently innovated how we think about analogical comparison and the way that it works in learning. Just when we thought we've settled down on one way of thinking about it, he comes in with another zinger and is really influencing the field and how it thinks about it. So, Dan Schwartz.
Crazy uncle, that's pretty good. Well, I started using contrasting cases 15 years ago, and my life is better. I'm 40 pounds less, my IQ's gone up. So behind contrasting cases is induction. So I thought I'd talk a little bit about induction to get us started. So there are usually two senses of induction. One is information pickup, and it's sort of the analog of a magnetic field inducing a current in a coil. So it's this sense of information pickup. So for example, you might look at this dog and you're trying to decide what's important about it. If you have a set of contrasting cases around it, it helps you to pick up the distinctive information. If I gave you some time, you'd start to notice that it's the ears. And this is how you identify this dog. So this first sense of induction is noticing or picking up distinctive features that you might otherwise miss. So it's the tasting wine side-by-side idea. The second sense of induction is finding a rule from instances. So this differs from deduction, which is deciding if an instance is derivable from a rule. And it differs from abduction, which is given an instance deciding which known rule fits that instance. So legal reasoning is abductive. You get a particular crime and you decide what precedent does it belong to. So induction's different. It's about finding a rule in the first place. So it's sort of the heart of discovery, right? And so it has these two senses. One is discovering the features of the world. The other one is discovering sort of a rule to explain those features. So the induction researchers largely examine these two senses separately. The area that's worried about information pickup has been perceptual learning. They use words like gradient, optic flow. The other area has been sort of categorization, concept, attainment, analogy. There they talk about things like necessary and sufficient. So they're really quite different lexicons and different research traditions. But it turns out they work together very well for an instruction. And arguably, they're the same thing. But Dedra left, and I don't want to have the argument. So later. So let me describe my version of contrasting cases. The classic is tasting wine side by side, and you begin to notice it. When I moved to California, I discovered it wasn't just white and red. So after doing lots of studies on contrasting cases to teach, we sort of stumbled on this sort of highly concentrated format. And so this is an example. I was a middle school teacher, so fun is important. So what this is this is to teach density. And what you have companies that ship clowns to parties. And each company always crowds their clowns the same amount. And you want to know sort of a crowdedness index for each company because crowded clowns are grumpy clowns, and you don't want to hire the most crowded companies. So these are contrasting cases. Here, a lot of kids will start on and say, well, this top one is a 2. That's how crowded it is. It's a 2. And then by looking across the cases, they begin to go, oh, 2's not going to work because that bottom one is a 2 as well. And then they would sort of look and notice, well, 2 compartments isn't going to work either because that bottom one also has 2 compartments. So these contrasting cases help them begin to notice features that they might otherwise gloss by jumping on the thing that's the most obvious. So that's for the sense 1. The sense 2, each of these is a proportional relationship, right? So the top one is 1 clown per bus compartment. The middle one, it's 3 per compartment, and the bottom one is 2 per compartment. And so the goal is for students to recognize that the key is a ratio, and that the difference in that ratio is what comprises density. So here's just describe some brief results from a pair of studies in regular science classes. They both had about 128th grade students. Both had very similar results. Both are targeting what I consider the big idea in middle school science, which is ratio. You see it on Cartesian graphs, percent, but a lot of the science content involves ratio as well. So half of these 8th graders were in an inductive treatment. They had to invent an index to determine the crowdedness used by a company. And so about 90% of them found the rule. They were working in pairs. The other half of the 8th graders were in a non-inductive treatment. We told them the density formula with some examples, and we gave them a worked example to show how you find it. And then they used the exact same worksheet to practice. So they found the density for each of those companies. And so 95% of them used the rule correctly. So they learned the formula we told them. So 24 hours, we simply asked them to redraw the worksheet. So they had this, this picks up this sense 1, this information pickup. What did they actually see in that worksheet? So here's a little piece of the worksheet. And here's an example of a drawing afterwards that's very low structure. So this student did not pick up the density relationship at all, right? You can see they've got sort of, it's those two buses don't have the same ratio. This student does much better, right? So they've got the 1-to-1 for that. So when you look at the percent of students by condition, the non-inductive students, about 1/8 of them actually saw density. Most of them were just doing division, but they didn't actually see density as a quantity in its own right. The ones in the inductive condition do much better. So they find the fundamental property of density is this ratio. So sense 2 is learning a rule from instances. So the first one was, did they even see it? The second one is, did they learn a rule that they could use somewhere? So they completed some more activities like this in the same treatments, 1 on density and 2 on speed. And they received a lecture and formula practice on these things. And both groups were the same on a computation post-test. So they all learned how to push the formulas. But 3 weeks later, the teacher gave them a semantically far transfer task. And so their task, given a sheet like this, was to determine the stiffness of the mat fabric. And so this is the spring constant. It's a relationship between the amount the fabric stretches and the amount of mass that's on it. It's represented by a number of people. And so you need the 2 together. You need the ratio to do well at this. So here are some sample solutions. The one in yellow is a good one because it takes into account both the mass and the distance, the number of rungs the fabric stretched. The one in the upper left only pays attention to the mass. The one in the upper right only to the amount of stretch. And the one in the lower right uses almost stiffness, which is a fairly common answer. So here, there's a lot of ways to partition this data. Here's the results for the non-inductive condition by prior science achievement, split low and high. So you can see the low students aren't doing as well at seeing the ratio in the trampolines. If you look at the inductive students, they do much better. So they're transferring this idea of looking for a ratio. And as you see, the low inductive students are doing as well as the high tell-in practice students who were told the answer first. So that's important because a lot of people worry that discovery activities should just be for the smart kids. And that's just not true. So to recap, the inductive plus contrasting cases, students pick up the relational structure and they use the structural rule to handle new situations. The non-inductive plus contrasting cases, the students learned the rule. I mean, we told it to them, but they never saw the structure of the cases, which means they can't spontaneously recognize when to use that rule. I think the second condition is important because it's a cautionary tale for flipped instruction. You may have heard of this. The idea is you go watch the lecture at home and then you come in and practice at school. The problem is if you tell people things too soon, it gets in the way of induction. They're paying attention to what you told them, not the situation that they're supposed to figure out. So you should let inductive activities prepare students to be told. Telling them first will stop them from noticing what's in the environment that they're supposed to learn. Okay, so that's the basic argument for why induction is good. So now, how do you make good cases? Sort of what kinds of instances can you put together that support both senses of induction? So for information pickup, we try to get near comparisons so they can notice precise details, so use near instances. This is what Dedry was talking about. But when you go for rules, for a general rule, you tend to use far instances so they can locate what's unique to both of them and ignore sort of all the extraneous stuff. So how do we put these together? Well, this is kind of an important but neglected question. I think a lot of cognitive psychology is worried about what's in your mind, not so much what's in the world and how you design a world for you. So how do we pick examples that optimize induction? A lot of problem sets in books are based on intuition, not theory. But this is a very familiar question in perception research, which asks, what's the information structure such that people can come to know it? So here's an example of perception researchers who've done enough work at understanding what is the nature of the world such that we can see it, that they can use a computer program to recreate this gradient that looks in 3 dimensions, even though it's on a piece of paper. So they've really figured out sort of what it is that makes it so we can see things. So we need to do the same thing for instruction. So let me give an example of why this matters. Here, this is a study with community college students who are strikingly like middle school students when it comes to math and science. They have different motivations, but you know, they're, as my colleagues at the community college say, they're kind of Swiss cheese. And so here they're learning about inelastic collisions, momentum, things that collide and don't bounce back. So like a 1,000-ton train going 1 mile, hitting a 2-ton car going 50 miles, who wins, right? And of course, nobody wins, but the train will push the car backwards. So the experiment involved the structure of the contrasting cases, and there were 2 conditions, and the study's about 2/3 done, but I'll share, and you can't tell anybody, except for Nicole, who'd be very proud. So here's an example of the worksheet. They have to invent a procedure to predict whether a new case will stop, go right, or go left. And so we give them these cases, we tell them the outcome, and their job is to figure out what seems to be the rule that makes the difference. And then afterwards, we tell them you have to predict some new ones. So this is for one condition. This is the main effects. So this problem, you know, it's sort of easy. The other condition got the interaction problem. So instead of this problem, they would get this problem. So here's another example. This one is easy because it's a main effect. It's, you know, more crates wins. The interaction condition got this instead. Right, so, and then here's one more example. This is one where the main effects condition sees speed wins, right? More arrows means faster. And then the interaction condition got this instead. So basically, if you're in the main effects condition, you're learning that the number of crates matters, the speed matters, but you're not learning that they can trade off. The interaction condition, you get examples that allow you to see they trade off. Afterwards, they received 18 new problems, and they had to predict what will happen. Will it go left? Will it go right or stay the same? We used Seiler's rule assessment. Several were these interaction problems, like what happens if there's 3 crates times 2 speed versus 6 crates and 1 speed. And so this is what you get. If the students worked on the interaction cases, they do much better on the post-test than if they only got the main effects cases. So a more detailed analysis, basically the main effect students only get the main effect problems on the post-test. So anytime there's an interaction, they don't get it. The interaction students do quite well for the most part. So a little more to the study. All the students received a new set of cases on balance. And both groups got identical cases, contrasting cases. And all of them included the all-important interaction cases. So they got problems like this, right? And so here are main effects cases. You can solve it by either looking at distance or weight. You don't have to think of a relationship between the two. Then there's the 3 interaction cases, right? Where you need to come up with some relationship between weight and distance. So even though both groups get perfect cases, you can see that the ones who got the main effects for the collisions, they miss the interactions. Because they've got this main effects rule, it stops them from actually seeing those interaction problems. So they've got a negative transfer here. If you get it wrong, it sticks. There's another condition that was controlled that just did the balance scale with no training. You can see they do better than the students who had the cases that didn't sample the space correctly, and they then transferred that incorrect knowledge. So induction is psychologically powerful. Once a rule is in place, it's hard to get students to engage in sense one or picking up new features. This is the same problem we saw with the crowded clowns. Once you have a rule in mind, you think you know everything, and you don't bother to see what else is to be learned. So the sampling of cases that you give students to learn from, this seems obvious, but it's not covered in the literature. And so we're working to develop a principal procedure for picking instances that works for multiple domains, not just this sort of ratio domain. Inductive attitude, compare and contrast doesn't work. Students need to be searching for a general principle. And so induction is hardly touched in instruction, being central to practicing scientists. It shows up in the early grades as observe closely, but in the higher grades you see nothing that treats induction, and it's not an activity. Generally, it's control of variables is the scientific practice. We tell students general principles. It doesn't mean they understand what it takes to make one. This is just a deep missing epistemology in science students. Here, I'll just give you a quote. This will say it all. This is what one student did. You may think that's funny, but you do it too in your own life. This is it's a very scientific attitude to think that you need a single explanation for many, many things. It's often easier just to have a pretty good rule and lots of exception cases. So right now, we're trying to fix this up. So stay tuned. So wrap up. Like reinforcement learning, induction is powerful for good or bad. There's 4 key issues. One is you need a way to determine the best variability for the contrasting cases. Wrong instances can block induction or entrench a wrong rule. You need a way for students to learn the idea of a general principle. Key goal of science is generalizable knowledge. We don't teach it. We don't assess it. Students don't know what to induce when they're given these tasks. What if students don't discover the principle? What if they don't make the right induction? It's a minor issue, right? The inductive activities get them to begin to notice the important features, so when you tell them, it all makes sense. Finally, tell and practice, the most dominant approach to instruction. The MOOCs are taking this to scale, sort of the worst model of instruction, lecture and then go home and practice. It's being brought to hundreds of thousands of people now. Better sequence is to have them try and do induction, then you tell them, then you practice. So these are highly concentrated contrasting cases that can make very good starter units. Thank you.
So I think we have time for a couple of questions.
No.
Dan, with that fascinating work with the trains, have you thought about trying a transfer condition where eventually you do have to learn to work with the formulae because, like, how much speed beats how much weight, et cetera, et cetera. Do you think that the group who see the interactions would be better prepared to actually learn the formulae?
Yeah, this is older research where we show that if you have a certain kind of experience, it really prepares you to understand the formal treatment much better. And it also helps you understand formal treatments on subsequent topics because you understand sort of the underlying. So we did this with Faraday's law and magnetism. And one of the ways we found out is we asked them, I don't know, this is too obscure, but basically we asked them why you take the dot product, which is to get the X vector, which is what causes the induction of the current. And the students who are told, but without doing the induction, don't know the answer to that. The students who induction say, oh, it's to get the X vector so you can find the normal force. So in general, these activities prepare students to learn the formal treatments quite well. If you give them the bad cases and you give them the formal treatment, I haven't done that yet. My guess is they wouldn't understand why you're multiplying for momentum. They just copy it, be my guess.
Another question?
See, I'll have you know they're both from the competing NSF center. So this is.
We think of ourselves as one giant SLC enterprise, right? Anyway, my question is this issue of kids getting the main effects and then failing to be able to get past that. That's really, I mean, that seems like a very important issue because, of course, there's often a sort of reasonable, or let's say what sounds like a very pragmatic, reasonable way to go about things is first give the kids a couple of, starting principles and then make it more complicated. So my question is there any way to do that? For example, if let's say you're trying to teach a 3-year-old or a 4-year-old about balance beams. Could you, for example, get them to see the main effects and then say, but really life is more complicated, and sort of make some kind of I'm thinking of using language again, right? Use some kind of way to transition the kids into thinking about it differently.
Yeah, I think if you're with the kids side by side and they've got this and then they sort of come up with some explanation, then you give them a contrasting case and say, does it work for this one? And they go, yes, and you say it doesn't. Then you could have success. Here it's more spontaneous to see what they'll do.
Yeah.
So I do think there's a way to help students overcome this, although this is not irrelevant to misconception literature. Right, where you have all this experience with these very simple explanations. How do you get them to see that it's a little more complicated?
Right.
And you tell them, and you tell them. My guess is if you started over with sort of an inductive approach to help them see the contrasting case, it might help.
Yeah. Okay.
But this is really spontaneous. So it's,